So the current understanding of the electron and the photon is electromagnetic, but it comes in lumps. It's like a particle and a wave. And the electron is like a particle and a wave. It has particle-like aspects where it looks like a point, but it has wave-like aspects where it's a wave. So this is taken to be a kind of an accepted contradiction that everybody kind of lives with. Nobody really quite gets why, and this is why people say that quantum mechanics is not understood, because quantum mechanics is not understood. So at least people are not bullshitting, so that's fine. But that's the current situation. So how to fix it? Well, one of the things that people come up with is say, look, there's this contradiction between relativity and quantum mechanics. And there's quite a few papers about this. But in fact, it turns out, if you look into this properly, that where quantum mechanics came from was it came from relativity. And the guy who did this was a French prince called Prince Louis de Broglie. And poor guy was doing a thesis where he was having to look at quantum oscillations using relativity. And quite early on in this, he discovered there was a contradiction in the relativity as well. He found that in relativity, it's supposed to be the case that if something's moving, in a moving frame, clocks slow down. Twins paradox, the idea that somebody travelling at the speed of light coming back will not have aged, is one of the ideas of relativity. So you expect, by the relativistic law of slowing down of clocks, that if you've got a clock which is ticking, tick-tock, tick-tock, you move it to tick-tock, slows down, clock slows down, relativistically. However, it's also known that if you take a photon and transform that relativistically, it blue shifts, its frequency goes up relativistically. There's a relativistic Doppler shift. So relativity tells you that if you have a clock, it should slow down relativistically, tick, and it should also speed up relativistically. Now that's a contradiction on the face of it. And de Broglie set himself the task of trying to analyse that contradiction. And what he came up with was absolutely remarkable. He found out that it actually isn't a contradiction at all, that things can do both. Things can both slow down in time and speed up in frequency, provided certain conditions are met. And the condition that he found was that you could have an oscillation, that you could have two, in fact, what was happening is there are two distinct oscillations happening, one of which slows down and the other of which speeds up, one of which increases in frequency, the other which slows down in time. But they do it in a way which is such that if you look at the two waves at anywhere and at any time, the two waves remain in phase with one another. So if you have what's the phase of a wave? It's where you are on the cycle. This principle he called the harmony of phases, and this was a large part of his PhD thesis. This principle that the two phases had to be in harmony, despite the fact that they were actually happening at different changes of rates, is de Broglie's harmony of phases. And as a consequence of that, he found that if you had these two things were in phase when you're sitting in the same frame, and they diverged as you moved with respect to them. When you're not moving with respect to them, they both were at the same rate and hence always in the same phase. But if you looked at the same thing from a different frame, they'd remain in phase, but one would go faster, the other would go slower. Now, if that happened, there should be a beat frequency between them, and that beat frequency meant there should be an extra wavelength appears. It's like a modulation in electronics. And he could calculate what that modulation should be, and it turned out that the wavelength of that should be given by Planck's constant divided by the momentum. Lambda is h over p. Now, at the time, that was called the French madness. People just thought that's complete nonsense. It was just totally unaccepted until it was measured experimentally about 7 years later. At which point everybody went, oh my goodness. And at which point some theorists began to take interest, amongst them Schrödinger. And it turns out that if you take classical mechanics and you put this little relation lambda is h over p into it, and e is h nu, energy is Planck's constant times frequency, then what happens is that classical mechanics, and I used to do this in first year lectures, my first lecture in a fourth year class, you can derive quantum mechanics from quantum mechanics is derived from this relation. So far from relativity being in contradiction with quantum mechanics, it's relativity that originally led to the equation, which then is the equation you put into classical mechanics to get quantum mechanics. So this is the origin of quantum mechanics, lies in a proper understanding of how relativity works. And we'll see more of that later. So Louis did that. What we did, Martin and I did, or what especially I did in 2014, was to enshrine that principle in an extension of Einstein's relativity. And I call this absolute relativity. And what I did is I said, I'm going to invent this maths, but I'm not going to let the maths do anything unless it has the proper relativistic form associated with it. And it turns out that if one does that, and I've done it here in mathematics, so one takes this quantum mechanical formula E is h bar omega, and you know experimentally how that changes. If you look at a photon relativistically, you have this thing called the relativistic Doppler shift, this factor r here, and I can work out what that factor is from the relativistic Doppler shift, and it turns out they have these interesting, very interesting structures, and that I can rewrite the relativistic transformations that people use for space and time in terms of this Doppler shift. And if I do that, something very, very interesting comes out. And what's interesting comes out is that I can derive the relativistic gamma factor, which is the amount by which space and time shifts, by looking at this relativistic Doppler factor. And it has a very simple structure. This is the normal gamma factor, 1 over square root of 1 minus v squared over c squared. If I do that in terms of this factor here, it's a half of r plus 1 over r. Now, r plus 1 over r is this ratio of how much the wavelength shifts by. So what it says that the amount by which it shifts is whatever, so if it's a factor of 2, for example, that would be 2 plus a half. And a half of 2 plus a half is more than 1. It's 1 1/4. And that's the amount by which space and time shift. But what it means that if I take something which is made of circulating light, like my electron model, which is light going round and round in circles, and I look at the way that thing transforms, the light inside, it turns out that the mass energy of that thing transforms exactly, actually derives the Einstein formula for the rate of change of energy with velocity. In other words, relativity comes from the fact, if everything is made of light, as in Martin and my model of a long time ago, then necessarily those things that are made of such things obey this thing called relativity, Einstein's relativity. In other words, we derive relativity from the properties of light if everything is made of light, which we had conjectured that it may be so. So now, why is this important? It's important because this R factor is going to come back. This is the factor which you measure experimentally as to how a photon transforms in different frames. It turns out that from that one can derive relativity. In other words, stuff made of light transforms relativistically, or made of anything in any system. And that's going to come back. So this absolute relativity factor is going to come back in what's coming in what follows. So what is the new theory? The new theory, so the old stuff was a model saying that the electron might be a localized photon. What the new theory is asking what is everything made of? What's the quantum mechanical wave? What's it waving in? What's the structure of reality, the underlying structure of reality? At a more fundamental level than building block like Lego, sticking electrons and protons together. So what I've made up and put into the model are 5 and only 5 things. There's going to be a root square root energy. There's going to be space, x, y, z, and time. And the theory sounds completely crazy. What it is it's saying that that energy can take on different forms. I can have the energy as a flow in x, or a flow in y as a vector, as a motion, like a fluid flow in x, y, or z. So it can take the form of being something which moves along a line, or if I take two lines and bring them together, multiply them together, then it can also take an energy which takes place at a point. So the line can fold down to a point, certain processes. But also, I can equally take my line, and instead of folding it back on itself, I can fold it sideways. I can fold it sideways with a perpendicular line. And that produces something which is not a line, it's an elementary area, something which is a plane. So it's an elementary plane. And of course, once I've got a plane, then I could fold my plane back down to line, but equally I could open it up and fold it out to give me a volume. Now I've got 4 dimensions to play with, x, y, z, and t. So I have the point, I have the line, I have a plane. I can make out of 2 things. I can make a volume out of 3, but I've got 4, so I could also make a hypervolume, x, y, z, t, like a box, in 4 dimensions. If I've got 4 dimensions, you can make those things too. Now, so what I'm saying is that there's a dynamics which is described by these equations of the change of stuff. A line can change to a plane, or it can fold down into a point dynamically. I'm going to allow all of those things to be described by this maths. So I'm going to make up some maths which does that, whose language is the language of things contracting down from a line to a point, or from a plane to a line, but also going from a line up to a plane. And what I'm doing is I'm going to look at the interplay of that the energy contained in that, in linear flow, can fold out to a plane and become planar. And then the plane could become a volume. And then the volume could fold back down to a plane, which goes back to a line. And what's waving, what it's waving in, is a wave between these different space-time forms. Now, that's a load of bullshit and hand-waving, until you put it into mathematics. When you put it into mathematics, so I'm going to express these things mathematically. I'm going to develop a differential, a vector differential, which is the normal way you do these things. It turns out that what you get is you get a set of equations. And part of those equations are equations that, as a physicist, I recognize straight away. They're the Maxwell equations. And in fact, the Maxwell equations are the vector derivative equations of the planar forms. So D is a vector differential. G, if I make G just the fields, just the electromagnetic fields, and I do dG equals 0, then what magically comes out of all this bullshit I just told you is exactly the Maxwell equations. In other words, it's something which already describes a big portion of the reality in which we have developed the technology around us. Now that's so far so good, but the question is, do the other bits also mean something or not? They may mean nothing. It may just be that only that part, only the Maxwell part, has any meaning. The rest is just something that doesn't happen in nature. But what I've discovered is that quite a lot of the other parts of it are also already part of physics as it stands, and the new bits explain a whole bunch of mysteries that have never been explained by any theory before. So as well as reproducing the theory that we already have, and giving the constitutive equations of that parts of that theory, it also has new bits which open up complete new areas that couldn't be thought about before, and which turn out to start explaining huge areas where humans have just gone, what the hell is that, in the past. And that's why I think this is not wrong. Because when that happens, when it absolutely parallels what you already have, and opens up things that explain mysteries you never knew how to explain, it might not be the whole truth, but it's getting a long way towards it. So that's what this stuff is. So that's what we're going to put in. We're going to put root energy and the space and time. But not just space and time, but the possibility that we can have spatial planes and volumes, but also space-time planes and space-time volumes, and so on. So, and it turns out this is a generalization of electromagnetism, but also of relativistic quantum mechanics. Now, I could show that, but that's not for this talk at the moment. So 5 and only 5 degrees of freedom, 3 space dimensions, 1 time dimension, and an amount of root energy, of this root energy. Put that into a mathematics which is very close to a standard vector differential mathematics, slightly modified to actually restrict it to absolute relativity, to only do Einstein, only allow the stuff that we know happens in relativity. So it's actually a mathematics which is restricted. And this is important because if you've got the theory right, it has to just do what you see and no more. It mustn't give you things that you don't see. And a lot of the present theories do. They give you lots of stuff which is not observed. Glue balls. I spent quite a large portion of my life trying to find glue balls, because they should be there in the theory. We haven't found any glue balls. And I was looking for them 30 years ago, and nobody's found any since either. So it wasn't just me being useless. It's probably there's no such thing as a glue ball, despite the fact the theory predicts it. So strictly limit the allowed operations to what you observe by using absolute relativity. Space and time are the absolute basis. You're not going to allow anything else. Only space, time, and energy. Nothing else. No extra dimensions, no 11 dimensions, no huge number of elementary particles. I'm going to try and get all the elementary particles out of this. So, and to do that, I'm only going to allow the things that I'm using. I'm going to control that I don't allow any kind of addition. So, because some additions are not physical. So I'm only going to allow physical. What do I mean by that? I mean that, for example, if I have an electric field in the x direction, an electric field in the minus x direction, if you add +3 to -3, you get 0. But electric field has energy, and electric field has energy. If you add two lumps of energy together and get 0 energy, that doesn't conserve energy. So that kind of addition is just not allowed because it's not physical. So the kind of things you used to be able to do with maths, like adding 3 + 3 to get 6, no. If it's not there in reality, it's not there in the maths. Scrubbed, doesn't exist. So you're trying to speak a language which doesn't allow you to make mistakes. It's like Pascal. You're trying to find that computer language which doesn't allow you to make mistakes. So keep it simple. So what do you get? You get a maths with bits in it, and those bits are just what I just said. They're lines, planes, volumes, hypervolumes. And if you've got 4 dimensions, how many of these things have you got? So you've got 4 dimensions, you've got 4 lines in directions. How many planes do you have with 4 dimensions? Well, there's 4 dimensions. So you've got the xy plane, you've got the yz plane, you've got the zx plane. But you also got the xt plane, the yt plane, the zt plane. You've got 6. 1, 2, 3, 4, 5, 6 different planes. 4 lines give you 6 planes. So I've got 4 lines, that's 4. I've got 6 planes, they're the fields, it turns out. That's 10. 4 + 6 is 10. I've got 4 volumes, because if you've got 3 dimensions, you leave one out. There's 4 ways of leaving one out. So there's 4 volumes, that's 14. Then there's 1 point, and there's one 4-dimensional volume, x, y, z, t. So there are 16 degrees of freedom. And that's these things here. So the lines have got 1 index. So, for example, alpha I here is alpha 1, alpha 2, alpha 3. Alpha 1 is a line in the x direction, alpha 2 is a line in the y direction, and alpha 3 is a line in the z direction. So 1, 2, 3 is x, y, z. So, and alpha 0 is a line in the time direction, 0 for time, 1, 2, 3 for space. But if you've got that, then I can do combinations of this. I can do combinations of x, y, z with each other. So I can do x, y, y, z, zx. That's these alpha ij's. They have 2 indices, x, y, y, z, or zx. They turn out to be magnetic field. Then I have the ones with time and space, 0, x, 0, y, 0, z. There are 3 of those. So there's a 1 time, 3 space, 3 space space, 3 space time. Then there are 3 0 space space. So there's the xy plane, yz plane, zx plane with time. There are 3 of those, 3 of these. There's one thing with x, y, z, t, 0, 1, 2, 3. And there's one thing which is just the point, and that's your 16. All enumerated, and these are the, I'm only going to allow stuff which has that aspects in it. So you've got 16 different categories the energy can form. Planes, 6 planes, 4 lines, 4 volumes, 1 point and 1 joule point. So that's the stuff. And apart from those different forms, I'm going to allow an amount of energy, amount of root energy. So that's like a 17th degree of freedom. So I'm going to put the energy in, and the energy could appear as a line or a plane, or if it's a line, it can change to a plane. If it's a plane, it can switch to a point through going through a line, etc., etc. And these things are going to dynamically change into one another. So that's the maths. So you just made up some maths. and you've said the maths has to be strongly constrained, and it's going to be the maths of lines as they are, planes as they are, volumes as they are, measured to be. And it turns out that you don't need to do that, because when you put in the properties of Lorentz space and time, then all the other ones automatically work properly. You don't have to force them to, they just do. So that's great. Everything works properly relativistically because it's a relativistic basis you've put in. So, having done that, you define vector derivative in the normal way, which is a four-dimensional division. So that's this thing just here. You have the rate of change of this thing. How fast is this whole object changing in x? How fast is it changing in y? How fast is it changing in z? And how fast is it changing in time? So you look at all the possible changes, not just the thing, but how can it change? So if it's a line and it's changing in its own direction, it'll turn to a point. But if it's a line it's changing perpendicularly, it'll turn to a plane. Of course, a line moving this way is sweeping out a plane. So that's what they do, and that's what the maths does. So, okay, so what do you do then? Well, it turns out that if you do that and you let it act on the field, so you get this, and then you write down all the components and you look at them, you get this set of equations, this pattern, which is just the Maxwell equations, is what I said. So this machinery is made in such a way that it automatically generates all four Maxwell's equations. Now that's fine. You say, okay, great. We've derived the starting point of 19th century physics. Wow. However, it does have a slight advantage over, this is the standard textbook of Jackson, and if you look at what Jackson does with a tensor algebra just here, see, that doesn't actually work in a standard textbook. You only get half the Maxwell's equations. To get the other half, you have to actually put in the dual field, or you have to put in a totally antisymmetric tensor, which is another way to do it. But this approach is superior already to what you have in the standard, and it isn't page 1 of the textbook, it's some of the advanced stuff in classical electrodynamics, Jackson's standard textbook on electromagnetism. So it's nothing new, but it's kind of cool. It's kind of a nice way to do the same thing we've already done before. So nothing new so far. But the good thing is that the machinery gives you exactly what you always had, and which you know is right. So yes, we have a new theory, more complicated maths, put more in it, got the same thing out. Great. But of course, it's not just this thing, there's more to it. Now, sorry, this is horrible maths. So what we do instead of doing the thing on field is we do it on everything. And this is a printout from Innes's, this is generated by super stuff. We got some of the signs wrong, I had to change the signs, but apart from that, the LaTeX was generated by Innes's program, so it makes light work of that. But I had to do this translation, though. That's unfortunate, but never mind. Although he's worked on that too and got that partially working. So if you do this instead of just with the fields, which gives you Maxwell's equations, you do it with, instead of just the 6 areas, you do it with the lines, the volumes, and everything else, then you get this shit. And you can translate that into the normal form. And if you look at the normal form, what happens is the first 4 equations contain the Maxwell's equations, but they have some new bits, these P's and Q's. So wherever you see a P and Q, that's new. Wherever you see a B, that's just Maxwell's equations that we had before. So the extra bit you get here is those things which were points and which were 4-dimensional volumes appear as extras to the Maxwell equation. These are new equations, beyond physics as it stood. But you also get 4 more equations. These ones relate current and spin to one another, and these are complete new set of equations which are probably very interesting but are a shed load of work and which I've done almost nothing more than tell you about them. But they're there and they could be important in the future. I'm just going to concentrate on the first 4 and the extra 2 bits that have gone into it. So we're not going to look at all of, well, that's the same as that, but we're not going to look at the mass of that. We're just going to look at what happens to the light equations when you put, these are masses, P is a mass density. When you put mass in as a square root mass, and what happens is, I'm not looking at the equations for too long because they don't mean so much, right? What happens is you can start writing down solutions to the Maxwell equations. That's one thing, so not using the extra bit here. So one thing is if you write down this thing, this is not a solution to the Maxwell's equations, but this is what you do in absolute relativity. What that is this is a hypercomplex exponential, which is What does that mean? An exponential is a power thing, and the property of an exponential of e to the x, the main property of e to the x, or you can take as the defining property of e to the x, is it's that thing which if you try and change it, it doesn't change. It's like the derivative of e to the x, d by dx, the rate of change of e to the x in the direction x is e to the x, the function you first thought of. Now, why is that an important function? It's because that's a function that explicitly doesn't change anything. So it's a function that explicitly conserves energy. And there are a set of functions that are like this, and they're actually derived from this. And some of those functions are, well, the exponential function is obviously one, but some of those functions are the sine and cosine functions, the wavy things. So wavy things are contained in these exponential functions. There are ways of making the exponential function look like a wave. Now, we're doing quantum mechanics, right? And what's about quantum mechanics? Quantum mechanics has got wavy things in it, right? So, and these things kind of wave a little bit, but they don't wave properly. But what they have got is, the structure of this is a wave function that has a size, it's an exponential, and these funny things here, this alpha 3 and this alpha 0, it's the power of space and the power of time. Because what's happened is I'm trying to find out how this thing waves in space and how it waves in time. And if I put space and time in, I have to put a unit vector in space for the space and a unit vector in time for the time from this increase in relativity. Now that sounds weird because that's not what you usually do. You normally have a function that doesn't have a form inside the brackets. But mathematically, this is doing the same thing as you do by going to a complex exponential from an exponential, which turns a rising or falling exponential into a wave. But this doesn't work because it turns out that one of these things waves and the other one just exponentially decays. But it does work, it becomes a wave if you multiply the exponent by a volume, an angular momentum. Then both of these things square to -1, and the result is a wavy function. So we've got something here which has absolute relativity in it, in that it's got space and time, but it has an exponential which at the same time is spinning. So I'm thinking about an object which has a structure which is space and time, but that inner structure is then made to spin in spin space. And suddenly something looks like, well, what does it look like? So I take this and I do the maths on it, expand it out, and what I get is this function here, which is a photon wave function. If I then plot it out, here's the same function, once again, and here's what it looks like in electric. Now, first of all, the function transforms to being electromagnetic. Secondly, it does exactly what the Maxwell's equations do. It's a solution to the Maxwell's equations. And why is this so important? It's important because I've written down a wave function which, when you multiply it by another function, gives you something which precisely is a pure field solution despite the fact that it's derived from a mass. I have a coupling of something which looks like a mass field equation to something which is a pure field equation, like a coupling of field to charge to field rather, a generator of electromagnetic radiation from something that looks like a mass wave. In other words, I have a prototype. With this very simple addition of these two extra terms, I have a prototype object which can emit and absorb photons, which can emit and absorb electromagnetic radiation. Because I have the function for that electromagnetic, for that thing, multiplied by a simple pair of fields. This thing propagates light. And I get this function just here, which, doing that multiplication, putting that thing in, gives me something which is a pure field, which looks like, well, which is a solution to Maxwell's equations, which is exactly the same as the thing I started with, this curly thing going through space. So, just to recap, I've done something crazy. I've said everything's root energy sitting in space-time forms. I've done the maths of that. I've derived the equations I've seen before. I've used the principle I've used to derive those, absolute relativity, to write down some wave functions. Turns out those wave functions, when multiplied by another function, switch from being a mass field wave function to being a pure field wave function. In other words, they reproduce quite a lot of what happens in reality for an electron emitting or absorbing a photon. Transformation of something which is massive to something which is massless, a charge to a field. It looks like a charge interaction. And it's a solution to the electromagnetic equations that we always had before, which are d, this thing is equal to 0. So that object, although it looks very complicated, and it is actually pretty complicated, so it ought to look pretty complicated. If I let loose this Maxwell equation, right, which is this equation just here, then the answer is indeed nothing at all. In other words, it's a solution to that set of equations which we've had since the 19th century. That thing is a solution. This complicated expression here is a solution. But what's different about it is that solution is quantized. It's quantized because it's described by a single parameter r. And there's a universal parameter here. This describes not just one photon, but it describes every photon. It describes not just light, but it describes light that's confined within a rotation horizon to not be spread out over the whole universe. It describes light that's quantized and confined. It's, because of absolute relativity, something which looks much more like what you actually observe than the solutions to Maxwell's equations, which allow you to have all sorts of things that are not observed. It's constrained, the constraints have constrained the kind of solution to correspond far more closely with reality than anything in standard physics. So what you've done is you've put in something and you've lost a shed load of stuff. But what you've lost is all the stuff you don't see. And what you've got is the stuff exactly that you do see. That's what's left. So you put extra stuff in and lots of stuff come out because of the extra stuff going in. So that's the first result of the quantum bicycle project. This is amazing. I'm sorry. It is utterly beautiful the way that forcing the mathematics to do something which seems utterly horrible, making it follow a particular, making it only allowing space and time to appear with their proper vector space and times forms, quantizes stuff. That is utterly stunning. So, and here's the reasons this thing's a photon. It matches the experimental properties of a physical photon. It's a solution to the linear first order Maxwell's equations at once. Now, why am I saying this? Because the solutions you usually do, you don't do to first order equations, you do to second order equations by eliminating one field or the other. This does both at once, linearly. Wow, that's never happened before. The physical propagation matches the electric and magnetic handedness. If I take the electric and magnetic field of a photon, if E's there and B's there, the photon goes that way. If it's like that, the photon goes that way. Now, standard electromagnetism doesn't distinguish, but this one does. It only propagates if you flip one field, the thing goes in the other direction automatically. So that wave function propagates in the right direction for the physically observed handedness of the fields. Scales to any energy. That R parameter, if I take R to 0, the thing goes to oblivion. If I take R small, it describes every single photon from gammas to radio waves. So all of these things have the same angular momentum. So they're not quantized absolutely, but they're quantized relatively. So if one thing has an angular momentum, if I change as I change R, nothing changes. So, which is what you observe as well. All photons have the same angular momentum regardless of size. They get bigger, but they also rotate more slowly, and that cancels. And this also, as it gets bigger, rotates more slowly, and that cancels. Now, there's some stuff I didn't talk about, which is that matching boundary conditions here give black body quantization, which is part of quantization, but I won't get onto that at the moment. And lateral limitation, which is also something you want for a photon. So, that's what you get. You get better description of light out, and that's just for Maxwell's equations. I haven't put the and you get this propagator which couples photons to a mass field wave function. Now, what I'm going to do is I'm going to drop some more I'm going to drop Q. I had P and Q as well as the fields. I'm just going to leave the P in and see what the thing looks like. And this is the Maxwell's equations again with no Q's, but just with this P, just to see what that does. So I'm putting just mass in and not dual mass. And first thing to notice is the divergence of E in Maxwell's equations is the charge. Now, as soon as you put a non-zero P in, that divergence of E, if P is not uniform over all space, means that the divergence of E is necessarily non-zero. What that means is putting in this term introduces charge into the Maxwell's equations. So that's very interesting because that's a mass term. So the mass term gives you a charge through the differential equation. So electric field divergence is non-zero for if there's an exchange, if P is being exchanged for mass energy exchange, there's a non-zero divergence. Now, charge, as I said right at the beginning, charge in Maxwell is electric field divergence. Charge in quantum electrodynamics is a mass field exchange. Here's the coupling between mass field exchange, the view in quantum electrodynamics, and electric field divergence, the view in classical physics. This is both aspects of charge at once. The balance is there. Have the field divergence, you need the mass energy exchange. And there it is expressed as an equation. Again, new. More importantly, this only took 20 years to get this far. So, going past most of your lifetime, both of you, we were looking for something to make this thing go round and round in circles. Here it is. Putting this term in here introduces an extra bit into the momentum. Now the momentum in electromagnetism is given by E cross B, and E cross B is a vector pointing perpendicular to E and B. So for light, E is perpendicular to B and the momentum flows perpendicular to that pair. When you do the same product here, so introduce the mass here, so instead of doing FF dagger, which is what you do to get the E cross B term, which is this one just here, that funny X is a cross product, a vector product. What happens in the bivector part, which is the field, which is the momentum part, is that as well as having something going in the direction of E cross B, you also have a term which is in the direction of E. In other words, the momentum here isn't perpendicular to E and B, it has a component in the direction of E. And what that does for you is it means that any flow curves perpendicular to E, curves in the direction of E. So if you have something like this with E sticking out, then that flow curves. And that's the mechanism for it curving. You have the reason why it can go round and round in circles. You have the force that was missing before that confines the electron. Here it is, this term just here. So you have new equations, and the new equation has new solutions, and the new solutions are circulating light, and circulating light, as we know from the stuff we did in 1997, has charge and has spin a half and looks just like an electron. So there you are, Bob's your uncle, sorted. So this is the old stuff from 1997, so here's the twist, and here's this thing we've been talking about, and here's that flow actually drawn on a torus for you, so you can see what it looks like. So that's one of them, but you can see it's nested torus. This is old stuff from 97. And here is the whole thing on one page. So this is the quantum bicycle on a single page. How the electron and photon confine themselves, how they work. You have two twisting pieces of light coming in. They mix with one another. So instead of going left, 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 right, 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 they go left, right, left, right. They meet up with themselves. You end up with a twist that looks like this, and mode structure that looks like these loops for an electron and for a positron, for the same thing but the other way around with the field pointing inwards. So a pair of twisting photons, photon in, goes to a pair of circulating double looped systems, electron-positron pair, conserves charge, plus charge, minus charge, conserves energy, plus energy, minus energy, conserves everything. Energy wraps up into matter. You have the element of the electron wave function here, is this thing without a field prefactor. Stick a field prefactor in there, and the thing transforms to light, and you have the photon wave function. So there's a relationship between the electron wave function and the photon wave function, which is exactly that which you observe for physical photons. you have a new universal equation for the electron. Here's the ordinary Maxwell's equations. That extends to give this set of 8 coupled differential equations. And these are the Maxwell's equations plus mass and spin charge equations. And you also derive relativity from the properties of light. So you derive Einstein's relativity. From relativity you derive quantum mechanics. You have a paradigm quantum particle in the electron that has quantized charge, that has quantized spin, that has even the same g minus 2 of the electron when you calculate it. That's the anomalous magnetic moment. The pivot confines and is confined by the field to give you a self-confined system, which is the elementary electron made of light. But not only that, you also have the mechanism by which these self-confined objects communicate with one another by emitting and exchanging photons. In other words, you have a basis, which we didn't get into, for the theory of quantum electrodynamics. So the theory extends relativistic quantum mechanics, which I didn't talk about, but nonetheless, the equation of relativistic quantum mechanics is essentially the same derivative acting on some object plus ordinary mass, not square root mass. This one refines it by putting square root mass in there on the same basis of the fields, and it works better than ordinary relativistic quantum mechanics, and it's an even more beautiful equation, despite the fact that's one of the most beautiful equations ever written. So it slightly extends relativistic quantum mechanics. It contains Maxwell electromagnetism, and it derives the starting point of quantum electrodynamics and the relationship between the two different aspects of charge. So, apart from that, it also explains other things. So that's what the solution looks like. So that's the same thing as here, but now I've put the smoke disc in to show where the donut goes.